Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through this work 1, which is associated with energetics, all that idea on exothermic, meaning the reaction releases heat to the surrounding, or endothermic, meaning the reaction takes in heat from the surroundings. And all these are for the combined science, all the foundation science tier, and I'm just specifically covering through the chemistry contents of that curriculum. Okay, so let's get started. In this first question, we have a student who investigated the change in temperature. So we cannot see a change in temperature on a thermometer alone. But then what the thermometer does is it gives you an initial temperature at the beginning. And then when the reaction proceeded, the temperature would change. Temperature could go up, which means the reaction gives out heat. That's when the surrounding gets hotter. That means it's an exothermic reactions, or the opposite, where the final temperature, meaning the initial temperature, goes down, or it decreases, or it gets cooler. That is when the reaction or the system takes in energy from the surrounding. That's why we saw a decrease in temperature. So your final temperature, if it is higher, that is when we have an exothermic reaction. But if your final temperature is lower, if it is lower than the initial temperature, that is when we know we have an endothermic reaction. Okay, because the system takes in energy from the surrounding gets cooler. So here we are talking about the surrounding getting warmer because that is to do with the final temperature getting higher. So warmer is the same as getting hotter, whereas for this final temperature being lower than the initial temperature is when the surrounding gets cooler. If you look back at these questions, we will see this example where it says sodium carbonate and also ammonium nitrate dissolve in water. That's what the question says. In your syllabus specifically, in your combined science syllabus, it says candidate should be able to state that ammonium nitrate dissolving in water is endothermic reaction. But this is not in your syllabus for sodium carbonate. Nonetheless, these are practical investigation. So the student actually did the practical experiment, and there is a set of results which we are going to have a look at and try to interpret right now. So this student places 25 cl of distilled water into a polystyrene cup. So polystyrene cup is just one of those container which you can you put some hot drinks in there, but then they are very unstable on their own. So usually what we do is we put them inside a beaker. A beaker has got that flat end and therefore it's more stable than a polystyrene cup. So there's our cup there, which is the one inside. So we have some distilled water, and that is the first step. And then you put a thermometer to measure the temperature. So you have a thermometer. A thermometer measures temperature of the solution. This is the initial temperature in table 3.1. Initial mean at the beginning, at the start. So it's just before any reaction happened. So these are just the initial temperature. They're not exactly the same because, different batch of solution, different batch of water done at different times. Now she adds 2 grams of sodium carbonate and stirs the mixture. So now you have added 2 grams of sodium carbonate, you stir it so that it is mixed completely, and then she measures the highest or the lowest temperature reached, and then records it in this table. She washes it out, so she washes it out with water, and then she repeats the experiment. So she uses the same cup, but she put in new batch of distilled water in every single of this experiment. What is different? What is different is the mass of sodium carbonate. So here you can see you use 2 grams, 4 grams, and 5 grams. But altogether, you still use 25 cl of distilled water for each and every one. So here we get the highest or lowest temperature. This is 25.0. This is higher than the temperature at the start. So the temperature at the start has increased. It has gotten hotter. This is very clear an exothermic reaction. The change in temperature is your final temperature minus your initial temperature. So your final is 25.0, minus 20.0. Now you need to be very careful. If you put this on your calculator does not have a brain. Your calculator will give you 5, and that is wrong, because all this accuracy of the thermometer is to 1 decimal place. Your calculator does not know how to give it to 1 decimal place when it is 0.0. So you must have 0.0 in order to score that mark there. Because of your practical skills, you know how to read the data. Based on the data, 1 decimal place there, you got to have thermometer, the change in temperature being read to 1 decimal place there as well. Very tricky. Okay, so she repeats the experiment, and then 5 gram recording, blah blah blah. So we don't know about this one yet, but how about this thing here? What are we supposed to fill in actually? I have no idea. Well, we can fill in the last one, obviously. So that's 34.5 minus 19.5. Again, we have the same problem. If you do it on your calculator show you 15, and that is wrong as well because of the 1 decimal place accuracy in the data. You should read it to 15.0 for the change in temperature there as well. Not too sure about this yet, but let's just move on. Now we have ammonium nitrate. Just now was sodium carbonate. You're not asked on chemical formula here, but you know from your year 9. From your year 9, you should know formula: sodium ion, carbonate ion. The charge on the ion is the valency. And then when you crisscross the valency, these are year 9, even year 9 combined science students would have learned this, just like you would have learned it last year. So 2 of these means 2 of that, therefore I write 2 Na plus, 1 of this, 1 of it, so you get Na2CO3. How in the world do you get the formula for ammonium nitrate? Ammonium ion is NH4 plus, nitrate ion is NO3 minus. These are again in the table of ions stated in the year 9 chemical formula. The valency following the charge is just 1. The valency following the charge is just 1. When you crisscross the valency, you get 1 of each. So we get the formula ammonium nitrate being NH4NO3. In a practical investigation, it's very rare that they ask you on theory, but in a paper 1 or paper 2 kind of setting, in a theory paper, they can and they will ask you on chemical formula, they will ask you on reacting masses and all that kind of thing. Anyway, what do we have here? Can't work out the change in temperature yet, but we can work out the change in temperature for this one. You see the initial temperature is 20.0, but the final temperature has gone lower. That is because the surrounding lose the energy to the reaction, to the system, and therefore the surrounding lose the energy, the surrounding gets lower in temperature. So again, it is final minus initial. So what we get really is 12.0 minus 20.0. You could get minus 8.0 degrees Celsius. The negative there means decrease, and your temperature of your solution, of your water, decreases because the system takes in the thermal energy from the surrounding. This is the idea of endothermic reaction. This is an endothermic reaction for this second one. We know that in the syllabus, candidates should be able to state ammonium nitrate dissolving in water is endothermic. But here, sodium carbonate dissolving in water is not in your syllabus, but from the observation in this question, we see that the water gets hotter when you add in the sodium carbonate, so it's definitely an exothermic reaction there. Still can't fill in the blank, perhaps there are some information there. In fact, this is the instruction they give you. Read the temperatures to the nearest 0.5 degrees Celsius, record them like that. So I guess this temperature, we need to read them from the thermometer scale here. So this is sodium carbonate, 4 gram. Okay, so if you read it, you see that the thermometer read upward because you could see this is 20 and then going up to 30. So you know this is exactly 30 degrees Celsius. It falls on the line, so there's 30 degrees Celsius there. How about this next one? If you read carefully, this is in between that 2 small lines there. So what we have there is 16 And what we have there is 17, because you have 15 for this slightly longer line, and then 16, 17, 18, 19, 20. So this thing is in between 16 and 17. If you read back the instruction, read the temperature to the nearest 0.5 degrees Celsius. So we cannot read it as 16, we cannot read it as 17, we have to read it as 16.5 degrees Celsius for this particular reading for ammonium nitrate 2 gram. This next one is slightly easier. It is 10.0 degrees Celsius exactly for that 5 gram of ammonium nitrate. I think I'll fill in the ammonium nitrate table first. 2 gram for 16.5. 2 gram of ammonium nitrate for 16.5 there. So 16.5 minus 20.5. Do it on my calculator. Again, be very careful. Your calculator show you minus 4. It should be minus 4.0. Everything regarding temperature to the 1 decimal place accuracy to the nearest 0.5 degrees Celsius there, okay? But of course, they are not to the 0.5, they are just 1 decimal place, consistent with the rest of the data. For 5 gram of ammonium nitrate, I have 10.0 degrees Celsius, so I just put in 10.0 there. So 10.0 minus 20.0, I get minus 10 on my calculator. Again, by this stage, you should know that temperature to 1 decimal place, okay? And for the first one, we have sodium carbonate 4 gram and 30 degrees Celsius. That is actually wrong. I was wrong. It should be 30.0 degrees Celsius. Be very careful there, because they did say temperature to the nearest 0.5 degrees Celsius. 30 degrees Celsius is wrong. Read the question. Read your question. Okay. So that should be 30.0, which means our final temperature, 30.0, minus our initial temperature. Press your calculator, 30.0 minus 20.5, I get 9.5. This is not a problem on calculator because it does show you to the nearest 0.5 degrees Celsius. All these are negative, final minus initial, because of the change in temperature is a decrease in temperature, is an endothermic reaction there. So calculate the change in temperature for each one, yes. Put a plus sign before the values for an increase. So it's a final temperature minus an initial temperature. I would have lost marks if I didn't put the plus in front. So you could see that I put a negative in all of these, but I have not put a positive in all of these because we need to follow instruction. Plus, plus, and plus. The plus there indicates an increase in temperature. That is because your water, your distilled water, where you dip in the thermometer, it increases in temperature. It gets hotter because the reaction of the system gives out heat energy, gives out thermal energy, transfer the thermal energy from the reaction to the surrounding, which is the distilled water. That's why we see an increase in temperature there. And we have to put in the plus for an increase in temperature and the minus for a decrease in temperature. You got to read the question carefully, okay? So next bit, stirring the mixture. So we stir the mixture. It helps the solid to dissolve. Give one other reason why the mixture is stirred. Well, you know, you want the solid to dissolve, you stir. Just like when you're making a hot Milo drink, you will stir it in order to dissolve the Milo solid. But the other thing is, this is about distribution of heat, and we want the heat to be, distributed throughout. So we want to ensure the energy is not just being released at the bottom there where you mix in the solid, or they're just not resulting in a decrease in temperature for an endothermic reaction. So other than just to making sure that the solid dissolve, we want to make certain. So ensure means be certain that thermal energy, so this is thermal energy, or you could talk about heat energy, is evenly, or you can use the word uniformly. So it's kind of like equal essentially. Spread. How do I say it? Evenly or uniformly transferred. That's the better word, because even if it is absorbed or released, we use the term transfer of thermal energy. Evenly or uniform transferred throughout the solution. The solution refers to the water acting as a solvent to dissolve the sodium carbonate or the ammonium nitrate there. Now on the grid provided, plot the change in temperature. You need the change in temperature against the mass of the solid for both. So you need to draw one thing for sodium carbonate and then the other thing for ammonium nitrate. This is change in temperature already, final minus initial temperature. This is the mass of solid. Let's try for sodium carbonate first. So what do we have in our table? For 2 grams of sodium carbonate, we have 5.0, 2 gram and 5.0. So you will have your graph. You need to know how to plot a graph, yeah, okay? So they haven't provided you the axis on the x-axis. So I'm just going to draw in like this. So I have 0 and then 1 and then 2 and then 3 and then 4 and then 5. Let me just double check that this covers all the masses that I need for the ammonium nitrate. Yes, it does. 2 to 5, 2 to 5 there. In terms of temperature, the initial temperature are all 19.5, 20.0, 20.5, and the highest goes up to 30 or 34.5. So my highest is 34.5 and my lowest is 19.5. So I just need a scale that covers 19.5 to 34.5. I don't think they instructed us on what the y-axis should be. Oops, sorry, I beg your pardon, because these are temperature. They want the change in temperature, so I was wrong in that sense. The change in temperature is your y-axis, so we're looking at between minus 10 to plus 15, minus 10 to plus 15. So we need to be careful because we have minus 10 there. So on the y-axis, you need to be very careful. If I have minus 10, minus 5, and then 0, what else can I have? I can have 5, 10, 15, 20, like that, I guess. What else do they? No, they don't tell us what scale we should use. I guess this should be all right, minus 10 going all the way up to 15 or 20 degrees Celsius. Now let's have a look at the data again. So this is a bit tricky. 2 gram give you plus 5.0. So 2 gram. So 2 gram give you plus 5.0. So this is here. You put a cross for your point. So I should be very careful. I put a plus on all my increase in temperature there. Next up, I have 4 gram giving me 9.5, 4 gram and 9.5. So 4 gram and 9.5. So this is 5 and 10, which means this is 6. Every 2 square is 1. So 5, was it 9.5 or 9 just now? I forgot already. 9.5 for 4 gram. 9.5 for 4 gram. So 4 gram. So this is 5. This is 6, 7, 8, 9. 9.5 is just right there. Last but not least, you have 5 gram for 15.0. 5 gram for 15.0. 5 gram and 15.0, which is there. Okay, so that's it really for draw a straight line. So you just got to draw one line. You got to be best fit. So obviously you can see that they are not going to give you, like a completely straight line. It looks like a curve, but they want a straight line, just one, for the sodium carbonate, and label it as for just 1 mark. So we need to be careful. So I'm drawing this on the iPad, so on the screen it looks all right. Your job is not just to connect the first and the last dot, because here this is very far off, so that is not very good at all. What I would do is I want a straight line. A straight line of best fit does not necessarily cut through all the points, but it needs to be as close as possible to all the points. So I'm kind of like going through the middle bit in order to be as close as possible to all the points, rather than just connecting the final and the starting point, which is going to be a real mistake. This is part of experimental skills. You need to understand what is a line and what is a straight line. A means one. Best fit, you don't just connect the dots. It doesn't work like that. Okay, label the line as. So I'm just going to label this as. Next up, we should really finish off the other table, which is for the ammonium nitrate. 2 gram minus 4.0, 4 gram minus 8.0. 2 gram is minus 4.0, so 2 gram is minus 4.0, which is there. And then 4 gram is minus 8.0. So here's minus 9, here's minus 8.0. And last but not least, I have 5 gram of ammonium nitrate minus 10.0. 5 gram is minus 10.0. 5 gram minus 10.0. Again, draw a straight line of best fit. Label this line A. So it seems like this is a much better straight line, because here you could see, okay, it's not exactly cutting through all the points, but this is as close as I can get to all the points without just connecting the first and the last point like that. Okay, so your graph can differ slightly from mine as long as they are line of best fit. This is just experimental skills on plotting graph. Use your graph. Determine the change in temperature. If 3 grams of sodium carbonate, we are looking at line S, because sodium carbonate line was line S, 3 gram of it. So look at line S. I should really label this line A. Line A, because that's what the instruction given us in the previous video of the question. We're now looking at 3 grams of the green line, which is the line S. So this is 3 gram. So we're looking at around here. So 3 gram is exactly here, because there was 3 gram of the solid added. We would expect it to be, this is exactly in between plus 5 and plus 10. This is plus 7.5 degrees Celsius. So use your graph, show clearly on your graph. I already did that by drawing the lines to give me plus 7.5 degrees Celsius. Now the next bit is a bit harder. Predict what change if 3 gram of ammonium nitrate. Now you have 3 gram of ammonium nitrate, but instead of 25 cm cube, so not 25 cm cube, but 50 cm cube. So you have a lot greater surrounding. How you arrive at the answer when you add 3 gram of ammonium nitrate, what change in temperature? So this is 3 gram for the ammonium nitrate, so the blue line now. So this is 3 gram of these. Oops, I don't want to mess up my diagram. So again, I have 3 grams, but then if I just draw like this, but I will change this to dotted line style and make it dotted. All right, so you could see with your ruler, 3 gram of this ammonium nitrate solid will give me, give or take, minus 5.5. This is a bit tricky. Minus 5.5 minus 5.75 degrees Celsius, I guess, because there is minus 6 for every 2 square there. Minus 5.75 is for 25 cm cube of distilled water, because that was what you used earlier. So 25 cm cube of distilled water into that polystyrene cup, and then you add 3 gram of these ammonium nitrate, you expect to get minus 5.75 degrees Celsius. So, you know, minus 5.75 degrees Celsius for 3 gram of the solid ammonium nitrate for 25 cm cube of distilled water. Now, when you have more distilled water, so with more distilled water, in fact, how much more? We have double the volume. Double the volume of distilled water. You need to heat up. You need to heat up twice the amount. So same amount of energy. Oops, sorry, not heating, but it's taking in, right? So you have more water, and therefore same amount of energy taken in or absorbed by the water. Therefore, the decrease in temperature is half. The decrease in temperature is going to be half, because you have twice the amount of water to take in the heat. So there should be minus 5.75 divided by 2. That is going to give you minus 2.875. That is not rational because it's not 2 decimal place. I'll give it to minus 2.9 degrees Celsius, or you can really give it to minus 3.0, really up to how you read that particular graph there. So in this last part of the question, this student now repeats the experiment using some potassium carbonate. Earlier we used sodium carbonate. So we used sodium carbonate earlier. Now we use potassium carbonate. So what's the issue here? The issue here is that our temperature change kind of level off after a while. So, you know, there's no more temperature change. No matter how much extra potassium carbonate you add. So this graph, how you read it is, no matter no matter how much extra solid added, there is just no more increase in temperature. So no more increase in temperature. Why is there no more increase in temperature? That's what they're saying, okay? Up until that point, when you add more solid, you get greater increase in temperature. But from here to here, no change at all. No change in temperature. There is temperature increase. It is exothermic still because it's positive temperature change, but there's just no change in temperature. So since this experiment is about dissolving the solid in the water, if the solid doesn't want to dissolve anymore, therefore there will be no more temperature change. So it's very clear that at this point no more temperature change indicates that there is no more solid dissolving. So no more of the solid can dissolve. So this solid is potassium carbonate. No more of that solid can dissolve. That is what we call the solution is already saturated. No more of that solid that can't dissolve, or you can talk about the solution is already saturated. Saturated solution basically means that no more of the solid can dissolve because you already have the maximum amount of solute dissolved in that particular solvent, the distilled water, at that particular temperature. That's it really for these 30-mark questions. And yeah, don't forget to click the button on the bottom right to subscribe to my channel and follow me at ptet.chemistry across all the popular social media platforms to get connected. Thank you for watching. I'll see you in the next tutorial video.